Okay, good morning, everyone. I'm Utsav Neupane from the University of Kansas. Dr. Remy Lakin is my advisor, and Dr. Andres La Paz and Dr. Darwin from the advising committee. So the structures like high-rise buildings have large force and deformation demand, which results in high reinforcement requirements. That means we need to have a large number of bars at a given section, which creates construction and consolidation issues. And then this situation is worsened at the region of lattice splicing. So how can we solve this? We can use large high-strength bars, which reduces the number of bars in the same section. In the lattice splice region, we can use mechanical splices, which will reduce the congestion as shown in the picture on the right. But let's see what the ACI code says regarding their use. So in ACI, we have two different defined mechanical splices. There is a type 1 and type 2. In type 1, the bars being spliced develop 125% of specified yield strength, whereas in type 2, the bars develop 125% of specified yield as well as specified tensile strength. So as per the ACI 318 code, we can use type 1 splices. We cannot use type 1 splices with any grade of reinforcement in the critical regions. By critical regions, I am referring to the regions where the bars are expected to undergo inelastic deformations and yielding. We can use type 2 mechanical splices, but only with grade 60 reinforcement, and we cannot use lattice splices at all. So what we are trying to focus during our project is if mechanical splices can be safely used with grade 100 reinforcement at those critical regions. If yes, then under what conditions does the splice connection type and splice length affect the behavior at all or not? We will focus on using mechanical splices with different performance characteristics at the base of the wall, which is wall footing interface. We'll use mechanical splices with grade 100 reinforcement and fairly large sized bars, number 10 bars, and we will test the walls under displacement controlled cyclic loadings, and which our expectation is that the wall will have a drift capacity up to 3%. The drift is measured as the ratio of the displacement at the top to the height of the wall from the base to the loading point. Our project will look into three different types of couplers. The first wall looks at taper threaded coupler, which is a small length coupler whose length is around 2.5 to 3 times the diameter of bar. In this coupler, the bars being spliced are taper threaded, and then they are connected with the coupler using a torque wrench. In the second wall, we looked at switch threaded coupler. In this splice, the two bars which are to be spliced are first connected to two different ends of the switched coupler. The one end has a male threading and the other end has female threading, and then they are hand connected. The third wall will look at shear screwed coupler. In this splice, the two bars being spliced together will be inserted inside the coupler, and then the screws will be screwed into the bars until the head of the screws shear off. So the connection type is different in each of these couplers, and the length of the coupler also changes from like 3 dB to almost 15 dB. This is how the test setup looks like. The wall is 100 inches in length, 10 inches wide, and the length of the wall from the base to the loading plane is 300 inches, and the overall length of the wall is 30 feet. The wall at the footing is connected to the strong floor with the help of 10 pre-tensioned threaded bars. The wall will be prevented from out-of-plane deformation with the help of bracings at the upper and lower levels. The loading on the wall will be applied through the top block using hydraulic actuators, and the displacement at the top will be recorded with the help of string potentiometers. We also have up to track markers grid of 1 feet by 1 feet at the base to observe any deformations that the wall will experience. The wall wasn't cast vertically, the wall was actually cast horizontally, and then the wall was later lifted with the help of spreader beam and crane assembly. While lifting the wall and while choosing the lifting point, we made sure that no cracking would occur at the base of the wall so that the stiffness of the wall isn't compromised during later testing of the wall. The loading protocol on the wall is patterned after the FEMA loading protocol. It was loaded beginning from 0.2% drift all the way. It was increased stepwise until it failed. At each step of drift, it was loaded for 2 cycles, both in positive as well as negative directions. While testing our walls, we tested them under displacement controlled reverse cyclic loadings. While testing the first wall, the wall reached 3% drift, but the failure was initiated when we observed a first bar fracture at around 2.7% drift. And then because of this bar fracture, while loading the wall during the second cycle to positive 3% drift, the wall lost its lateral strength capacity and ultimately failed. This picture shows the condition of the wall at the base. The picture shows the front view as well as side view. So we removed the concrete from the base and observed how the fracture looked like. And we can see the bars fractured at the bar coupler section, and this occurred because of the reduced section caused by the threading in the bars. I don't know if it is clearly visible or not, but yeah, it occurred due to that reduced section because of the threading that protruded outside the splice region. Similarly, we tested our second wall with Suez threaded coupler, which was way longer than the first taper threaded coupler. The wall reached 3% drift per both cycles to the positive direction, and then in the negative direction during the second cycle, the wall observed a brittle failure. So from this picture, we can see the concrete in the boundary region just blew up, and this was resulted due to the shear-induced compression failure. It looks like the wall had a outer plane failure from the side view, but it was like resulted due to the shear-induced compression failure. We also removed the concrete from the base, and no fracture of the bars was observed. The failure region shifted slightly above the base compared to the first wall because the coupler length itself is way longer than compared in the first wall, so all the damage was concentrated right above the coupler region. From this preliminary test, what we can conclude is walls with couplers that cause bar failure or bar fracture away from the splice region. In direct tensile test, we'll have deformation capacity, a drift capacity similar to the walls with continuous bars. In the future, we'll test our third wall with shear screwed coupler, and then after detailed analysis, we'll propose qualification requirements for use of couplers in special structural walls. I would like to thank our primary sponsor, EPRI, and other sponsors. I would also like to thank ACI for this opportunity. Thank you for listening.